I started. Now you can introduce your the speaker. Thanks.
Okay. Well, thank you everybody for attending one more of our seminars. This is a seminar within the project of COVID-19 of the National University of Mexico, and you're very sincerely, we think this is going to be a very, very interesting talk. Our invited speaker is Professor Julien Arino from the Department of Mathematics of the University of Manitoba. And he's a member of the Data Science Nexus and a faculty member of VADA Graduate Training Program, and a member of the Canadian Center for Disease Modeling and the Canadian COVID-19 Mathematical Modeling Task Force. Julien is an expert in particularly known here in Mexico among the students in mathematical epidemiology on his work on, of the many things he does, but mainly the meta-population models, where he has done significant advances. And welcome all. One thing before we start, remember this is an academic enterprise, and the opinions of the speaker are his own and not necessarily shared by the National University of Mexico or the project. And the interventions, the questions will be at the end. And please, if you could turn off your microphone or your camera, so we have a better image of the transmission. And without much more saying, thank you, Julien. Please, the screen is yours.
Okay, thank you very much. Can you see my screen? Yes, I suppose.
Yes.
Yes, we can.
Okay, so I am going to speak about work on assessing the risk of COVID-19 case importations, and in relationship also with the efficacy of quarantine. And I'll make it clear that we're thinking about locations that are not seeing a lot of transmission, and I'll explain probably more in detail in a second. So I'll start with the end. I'll start with thanking people that have worked, etc. First of all, I will start by thanking you for having me. Actually, I would much prefer to be in Mexico right now, although we have good weather for once here in Winnipeg. But at the same time, the advantage of Zoom is that it allows me to be with you without being with you. So this is work that I did with Nicolas Bageux, who is a postdoc of mine, but who's now moving on to another postdoc, Stéphanie Porté, who is a colleague and also my partner, and James Watmore from the University of New Brunswick. And I'll point out that this is work that started because of discussions I had and questions I fielded from public health people from the Northwest Territories and the Yukon, which are territories in the north of Canada, as well as Prince Edward Island, which is a province in Canada. And this is work that's done in the context of a task, an external modeling group that has been set up by the Public Health Agency of Canada, and they provide a lot of help with this. So I just want to acknowledge their contribution for this. And before I go any further, in very small letters there at the bottom, I indicated that if you want to see the paper that this is based on or some code, you can go to medRxiv or GitHub and look for my name, and you'll find the information that is here. Okay, so my talk is going to be as follows. First of all, I'll talk a bit about the importation, the process through which a disease is imported, which I see as part of what I would call the spatialization of an epidemic. And then I will present the model that we're using to consider this problem, show you some results, and then I'll move on to the effect of quarantine, which is a slightly different way of using the same model to consider a related question. So first of all, in terms of how a disease becomes spatial. So what I mean by this is it's how it starts to propagate in space and time. And the way I think about it is summarized in this slide. So the idea is that there are 4 essentially processes that keep on repeating. If we start with a source point, which would be, for example, in the case of COVID-19, probably Wuhan. So from that source point, there is exportation. Let's start on the left. So after exportation, there is transport. When transport occurs, then you come to a new location, and there's 3 processes that happen within that location. First of all is importation. Then there's amplification, where the number of cases in the location, this new location, becomes larger and larger. And at some point, that new location becomes an exporter of a disease. So individuals infected with a disease start to loop back into the process and be transported to new locations. And my point here is really going to focus on this part here, which is the importation process itself. Because, and that, I was mentioning before, the Yukon, Northwest Territories, and PEI, these are places, the motivation for the work comes from them, because these are places that are quite isolated. So they have good control over inflows, and they had very, very few cases, and they were concerned about what is the probability that, you know, given all this disease around us, that we'll end up importing and that we'll end up with cases. And so that's what we're looking at here. So first of all, let me look at importation on the global scale. So this is a comparison of the spread of SARS and COVID-19 in terms of the number of countries and territories with confirmed cases. So these are ISO 3166 country codes, but there's also territories. For instance, Hong Kong has a code. And so this is the number of those places that are affected, that have reported cases, as a function of the number of days since the start of global spread. So in red, you have SARS, and you can see that the initial spread went about the same speed as COVID in terms of the number of places affected, but the number of places affected limited at 38, if I remember well, or 37 countries and territories. Whereas with COVID, at some point, the spread started to really hit most locations. And I think the last import that I could confirm from the data that I use was about 110 days after the start. And at that point, most places have imported COVID-19. But now let me look into a bit more detail, because I'm concerned about importing in a country. But if you think about countries, there are so many entry points that it's a bit more difficult. So here I'm looking at something more local. And so what I'm showing you on this graph is provinces and territories in Canada. So there's 13 of them. There's 10 provinces and 3 territories, and health regions in Canada, of which I think there's 122. And that's the percentage of these locations. So in red are the countries and provinces and territories, and in blue the health regions. These are the percentage of these locations that are infected, but have reported cases anytime in the past 3 weeks. So if I'm putting a dot there, it means location X has reported a new case, so a local transmission or an importation, but within the past 3 weeks. So this sort of filters out the sort of the noise that you would see if you would just looked at things day by day. Okay. So what you can see is that there's this initial spread. So this is only importations. So these are places, except for that little dip here, but these are places that did not have cases and then reported cases. And that initial spike here, these are not the number of cases, okay? It's the proportion of places that have cases. That initial spike is entirely driven by importations. So that means a location did not have cases, and then one day somebody comes from another location and is either detected or transmits the disease locally, and that local transmission is detected. So we don't know from that data which of the two it is, but this initial spread is entirely driven by importation. Then when you look further down, further closer to us in time, there's a mix there. There could be, at the moment when people had, jurisdictions had cases, it's also possible that during a 3-week period, what we are seeing is silent transmissions. So from here on, we don't really know if it's importation or silent transmission chains, but still many of these events, many of these times when we're picking up numbers are probably importations, okay? But without further epidemiological investigation, we don't really know. Now, what I'm going to do now is look at a model for describing this. So the idea is we use a model that has this structure. So it's a classic SLI-AR model, but we're thinking of things slightly differently from the way I normally do. So we're thinking about, okay, there's susceptible individuals. They might become infected. If they are infected, they go through a latent stage. And upon the end of their latent stage, they can either, and that's where it's a little, I mean, that graph is a little misleading. So they can be detected or undetected. So they can be asymptomatic or symptomatic or asymptomatic. But in this model, we're really thinking more along the lines of someone who is detected over the course of their disease. So it doesn't mean everybody right away would move to detected, but if at some point during your infection you are detected, then you would go through this top branch. Whereas if you do your entire infection without being detected, you would go through the bottom branch, okay? So detection is not really, I finish latency and then either I'm detected or undetected. These are more in terms of at one point, do I detect you or not, okay? The model itself is an SLI-AR model, so susceptible, latent, infectious, and asymptomatically infectious and symptomatically infectious. We're adding deaths to the model. And what I'm showing you here in blue, these are compartments where people are detected. So this is when you're looking at data, these are people that would be in your data sets. These are people that are either tested positive or have been tested and recovered or died after being tested or are being classified as having died from COVID after they died, okay? So this is a very classic model. I will mention, so if you notice, I have two of each of compartments, of latent compartments, infectious compartments, and asymptomatically infectious compartments. And I'll get to the reason for that in a second. I want to point out also that the infection term, that phi here, also it includes what is classic with epidemic models of the SLI-AR type, so infectious and asymptomatically infectious, but we also allow late stage latent individuals, so pre-symptomatic essentially, individuals to infect others, because this is something that has been noticed with COVID. Now, this is For instance, this is what I was saying, sorry. So symptomatic cases are those that are detected, asymptomatic are those that are not detected at some point during their infection. And that fraction pi here that you see that determines the fraction of people going the asymptomatic route is, in a sense, the non-detection, okay? So you have to see that pi here depends on your testing capacity as well as on the natural characteristics of the disease. So if I test a lot, my pi is going to go towards essentially the asymptomatic fraction, the true asymptomatic fraction of people that are not detectable or not detected at all. Whereas if I don't test, then I could have a lot of people going through A because they are neither, they could be symptomatic, but they're not detected, okay? Now, why the compartments? So this is a brief remark. The reason we put 2 compartments, and we could have put more, is simply to exploit the fact that if you have a model like this and you put more compartments, then you allow yourself to use, to obtain a distribution of times spent in like L, for instance, that would be Erlang distributed rather than exponentially distributed. So it's simply that we want to be able to, so if I had in this curve, the dashed red one is an exponential distribution of sojourn times, whereas if I have these more compartments, then I'm giving myself a possibility to have something that's Erlang, so where people don't change state quite as fast, and also where the tail is not as heavy as with an exponential. Okay, so because it's a model that we understand very well, we have access to things like the reproduction number or final size relations. I'm not going to go too much into that. I just point out that the basic reproduction number or the effective reproduction number is something we're using, and we have an expression for it. Although right away, what I'm going to do, oh yes, before I get there, okay, so let me just point out, if you look at the ODE model, the one thing we see which is important is that it's very sensitive on that value of pi. So this is a dynamic sensitivity analysis that we ran with the ODE model before. And we can see that in terms of long-term behavior, pi, which is the fraction of individuals who are asymptomatic, is the main driver of the behavior. Okay. Now, as I was saying, we have access to this effective reproduction number in the ODE case, but we're actually using not an ODE, we're using a continuous time Markov chain version of the model. Okay. So this is essentially the same, except that rather than focusing on what's going in and what's going out from a compartment, we focus on the arrows themselves. So the probability that a given arrow takes place, a certain transition. And so the way we consider the problem is like this. So we remember my aim is to understand the risk of importation. And the way I'm going to do it is that I'm going to take this continuous time Markov chain and I'm going to stimulate it by throwing a signal at it, which is people that are infected. And I'm going to feed these people through the system, perhaps after quarantine, and this is something I'll come back to later, but I'm going to feed people through the system and I'm going to observe the response of the system to this stimulation. And that's how I'm going to evaluate the risk. So first, let me briefly tell you what we think of in terms of stimulus. So for stimulus, we have 2 types. We have what we call a single stimulation, which is simply, I take an individual who's infected, whether they're latently infected, symptomatically infected or asymptomatically infected, often we take at random, but we can choose it whichever way we want. We start with one such individual and we observe the response of the model to the introduction of one person like this. Then we take the same context, but instead of introducing a single or a set number of individuals at time 0, we throw a sequence of individuals through to the system and we see how it responds. And so in terms of how we throw individuals, we're using a Poisson distributed inter-arrival time. Okay, so we suppose that there's arrival times T1, T2, etc., and that these inter-arrival times are Poisson distributed, and each time I'm throwing a certain number of individuals, and I observe the reaction of the system. So as I said, most of the time, we assume we throw in a single individual. I'll show you what happens when you throw in more than one, but most of the time, to keep things simple, we just say one. And also, most of the time, because we think of symptomatically infectious individuals as being detected, we assume they don't travel. And therefore, most of the time, we don't stimulate with I1 or I2 individuals, just L1, L2, A1, A2. Now, so that's what's coming in on the left. Now, what do we look for on the right? So let me make it clear also that we are looking at a time horizon of 3 months. We had to set something. Everything that I'm going to say, for example, in terms of final size, etc., is for 3 months. Now, the types of outcomes that I'm looking at is, okay, so first of all, I call importation anytime an individual arrives in your location that is bearing the disease. So that's an importation. But then the importation can be unsuccessful if that person, whether they're detected or not, that's another problem, but if that person does not contaminate anybody locally, that's an unsuccessful importation. Whereas the importation is successful if I have even one, I mean, it suffices for one transition of a local individual from S into L1. So somebody who's susceptible becomes latent because of this importation. That's a successful importation. But then afterwards, we're also looking at how severe successful importations are. And so I'm going to say they're non-critical, those successful importations, they're non-critical if what follows is what we've tried to represent here with a few little bars. This is a minor outbreak. So you see a few transmissions, someone comes in, they contaminate somebody else. There's a few cases, but eventually and quite quickly, cases die out. That's non-critical successful importation. Critical is you have what Whittle, so that's a paper from the 50s, Whittle called a major outbreak. And I'll point out that this is a very mathematical definition, which we can look for in our outcome, but that's one point where it's maybe a little annoying. And also I'll point out that by the definition of Whittle, of a major outbreak, there cannot be a major outbreak for him, and therefore for us, if the effective reproduction number is less than 1. So if the effective reproduction number is less than 1, we have only minor outbreaks if we have an outbreak at all. And if the basic reproduction or the effective reproduction number is bigger than 1, we could either have a critical or a non-critical successful importation. So let me show you the results. So first of all, as I was saying, most of the time we throw in a single individual, infected individual. This is what happens if we throw more than one. So the leftmost column of results there is if I throw a single individual, and then as I move towards the right, I'm throwing more and more individuals. And here, to make things simple, I'm assuming I'm throwing individuals who are in the first of the 2 latent stages, so L1 individuals. And you can see that, so we're looking at different values of RT. And okay, so I should make one thing clear before I go any further. We're thinking of what happens when we throw cases in, but obviously your local conditions in the place that is potentially an importer of a disease matter a lot. So if you have very good contact tracing, if you have very good isolation, then a single case is very likely to stay a single case. But if everybody is mixing with everybody else and your RT is large, then a single case is very likely to go bad. And so when we change the value of RT locally, we're thinking of this as representing the strength of the public health intervention. And what you can see is that whatever happens, as soon as you throw in sufficient number of people, infected people, every time you import, you're almost assured an epidemic. Okay, a major epidemic if you're looking at R0 bigger than RT bigger than 1, or a minor epidemic if it's less than 1. But whatever happens, there's a large, the size of the import is important. And I mention this because this is linked, for instance, with what happens on board a commercial flight. If I have one person boarding the flight, but on arrival, he or she has infected 10 people, then this puts me from an import that would be here at 1 to an import that eventually will be of size 10. And you can see how important that is. The second thing that I want to show you is in this graph, which shows you how the probability of a successful importation, so that's the background color that you're seeing, the grays, and the attack rate, that's the percentage of the population that's infected over a 3-month period, remember, that's in percent. So this shows you how these things change as a function of the average number of days between importations. So here I'm looking at these Poisson process of throwing in new cases. And so 1 over the Poisson rate is this average number of days between importations, and how much of an effort you're making to control the disease locally. And you can see that if importations, so if I'm on the lower left, lower right here, this means that I receive cases on average once every 50 days, I will have an importation. And also, if I'm on the bottom here, I'm doing a very, very good job at control, at social distancing measures, masks, etc. So my RT is at 0.5. Well, there, my probability of a successful importation is of the order of 0.4. Whereas if RT increases, for instance, so my control measures are not quite as good, you can see that the numbers are going up. And more importantly, as I go across in terms of the average number of days between importations, I also see an even more marked increase. So these red lines, I don't know if it's really visible, these red lines are the level lines for probability of a successful importation of 0.4, 0.5, 0.6, 7, 8, 9, and 99. So you can see that they become more and more vertical, which means that the big influence is really that way. Okay, if I move left, so if the average number of days between imports goes down, my probability of a successful importation increases. And for example, when I'm here, it doesn't really matter if I import a case on average every 10 days, it doesn't really matter how much of an RT I have, so how much of a local social distancing measures strength of NPI I have, because virtually everywhere I will have a high probability of importation. On the other hand, what the attack rate shows you is that the RT is still important. So it shouldn't, like public health authorities cannot say, oh, okay, I'm doomed. I'm getting a case every 10 days. I can just let things slide, because what you can see is that the attack rate, on the other hand, which is these dots, the attack rate increases a lot with RT. So whereas you have essentially the same probability of a successful importation wherever you are on this vertical line, at the same time, when I'm here at the bottom, my attack rate is quite low. That means that I must be around 0.01. That means that 0.01% of my population will have been infected after 3 months. Whereas if I'm up here, then I'm more in the 5% range or something like this, which means a much, much more important impact. Okay, so the two things are playing. Here I'm showing you, I won't spend time on this. This is the same graph, but I'm just looking at the proportion of critical successful importation. So here, as I said earlier, this only happens if you have RT larger than 1. But what you can see is that the situation is not as clear-cut as in the other case, and actually still, most of your import. So what this says here, if you're below 0.1, which you are if you are here, this means that most importations will be successful but non-critical as compared to critical that they are here, which is good as well. So this is another way of saying, yes, maybe that probability of importation depends a lot, or of a successful importation depends a lot on the average number of days between importations, but RT does play an enormous role in the severity of the importation. Okay, so now let me switch to the effect of quarantine. I'm almost done. Now, we were playing with the model, and at one point we realized that one thing that would be interesting would also be to consider quarantine. And so we're looking at a sub-model, essentially, of that model that I presented. So here, I'm going to think, okay, what is it for quarantine to be, what is a good quarantine? So essentially, a good quarantine is one where if you are an import case and you're an unobservable import case, so you are latent or you're asymptomatic, so you're not detected. If you're an import case, at the end of your your quarantine period, if you're still unobservable, then you might join the population, the general population in the place that you come to, and contaminate people there. So that's an unsuccessful quarantine, because you come in, you're infected, at the end of your quarantine period, you're still infected, okay? So the way we do this, and the quarantine is successful if anything else happens. So if you enter in one of these 4 stages that are unobservable, but you leave quarantine in any other stage, even in dead, the quarantine is successful. It's unfortunate for the dead, but they are not contaminating the population. So the quarantine was successful in this sense. And the way we do that with the model that I was showing you is very simple. We think of the continuous time Markov chain model, and we turn off propagation. Because if you're quarantining, and I should mention, we're thinking about perfect quarantine. You're staying at home, you're not seeing anybody, etc. So I turn off propagation. I put beta equals 0. That means you're not having any interactions, but you're still living your epidemic, your infection within my tree of possibles. That is the model. And what we do is we take TQ to be the number of days you spend in quarantine, and we look at what state you are when you come in and what state you are after TQ days. Okay? And so RT doesn't really play a role here, except insofar as RT also depends on epidemic parameters in terms of how long you spend incubating and things like this. But transmission doesn't play a role, okay? So let me show you the type of thing we see. So here I'm showing you infection trajectories, so to speak, for 7 and 14 days quarantine. So both of these graphs, let me explain quickly. On the left are those 4 unobservable states, L1, L2, A1, A2. So, and each of these is 10,000 simulations. I should make, so it's 2,500, I throw in 2,500 A2, 2,500 A1, 2,500 L2, and 2,500 L1. And what you see here, the dark gray curves are the individuals who were in one of the dangerous states, where, so undetectable states when they entered quarantine, and who are still in one of those states at the end of their quarantine. Whereas the light gray ones are, for example, these are individuals who entered in the second stage of the asymptomatic period and finished as recovered after their asymptomatic period. So they're recovered, they leave quarantine, they're not harmful to others, okay? So this is for 7 days, and you can see that there's still quite a fraction of people that are in the at-risk categories, or at-risk for others categories, I should say. And this is for 14 days, and you can see that 14 days has shrunk quite a lot, these dark gray areas that represent people that are still a danger to others. And the efficacy of quarantine is then this number that we call C, which is 1 minus the probability that the quarantine is unsuccessful. So it's the probability that the quarantine is successful. And C, of course, depends on how long you spend in the compartments and the probability that you're an asymptomatic or an undetected case. But we can actually, so I was saying before that this graph here I've obtained by doing simulations, but we can compute it actually explicitly. And I'm not going to detail too much. I mean, I'll just point out. So because we have no transmission, we can look at the model, and the model is linear everywhere except for transmission. So it's quite easy to look at it. And so here we have, we write the matrix T of transitions between stages of infection. So for instance, I'm in L1 and I'm still in L1 at time, sorry, that's the rate. So this is the rate of moving from L1 to L1, which is actually the opposite. It's the rate of leaving L1. And so I should read by columns, actually. This is L1 to L2, L2 to L2, which is the rate of leaving L2. But from L2, you can go into I1 or to A1. Okay, so by columns like this. And so if you look at this, you can write this as a differential equation where if I have a vector of probability that individuals are in a certain stage, this vector of probability satisfies this differential equation. And we can just solve it using the matrix exponential. And so we have actually an explicit expression or computable expression, a computable explicit expression of the efficacy of quarantine. And so this is what I'm showing you here. This is the duration of quarantine and the efficacy of quarantine as a function of, so I'm going to say this the wrong way around. This is the efficacy diminishes as pi increases. So this is for increasing values of the number or the proportion of individuals who present symptoms, who are undetected. Okay, so we can compute this explicitly. Okay. Now, let me show you the last thing I want to talk to you is estimating lambda, which is that rate at which cases arrive, and the link between this and the efficacy of quarantine. So very simply, we estimate lambda by looking at the following thing. So we say, okay, so if I'm in a given location, I can estimate the rate at which individuals from another location, the origin, I, arrive, and that rate is multiplication of the fraction of active cases in the population at the origin, multiplied by the fraction of undetected cases among the active cases, and multiplied by the number of passengers or travelers per day coming from I into the destination. And because these are competing risks, I just need to sum to get the lambda for me as a location. So if I'm looking at people coming from various places into Winnipeg, I will compute individual lambda i's for each of these locations, and just summing them gives me the average rate of importation. So an example, we did this sort of thought experiment with Prince Edward Island. So they set up what they call the Atlantic bubble, and on that day, 8,500 people went into PEI. There's a single way to get into PEI from mainland Canada, except by airplane. It's by, there's one road, which is a bridge. So it's very nice because we know how many people go. And so we sort of did this thought experiment. We said, oh, suppose that all these people are coming from New Brunswick, because that's where the bridge starts, and that this happened at the time when New Brunswick had the highest number of cases at that point. And in that case, using the formula before, well, we find that the average time between importations is 6.4 days. Okay, so in practice, when they did this bubble, just for this is a thought experiment. In practice, there was one active case in New Brunswick. So that means that that day, the average time between imports was actually 460 days, which is much better. And so what that tells me is that that's where I was in that hypothetical case. That's where I was on the day of the opening of the bubble. And now, what does quarantine do to that? Well, quarantine plays on the rate of importation using this very, very simple formula. So if I call lambda the rate of case importation and lambda q the rate of importation regulated by quarantine, by the fact that people go through quarantine, and C is the efficacy of quarantine, then that lambda q is simply 1 minus the efficacy times the original rate. So this is what I'm showing you here. This is what we have, this bad case estimate of what the import rate would be in PEI. That first vertical yellow bar is what happens if I apply a 7-day quarantine. And that second one here is what happens if I apply a 14-day quarantine. And you can see that I've shifted things quite appreciably to the right, which means that my probability of importation is much lower, and so is my attack rate. Okay. I'll just point out that, I was saying, so the travel rate comes into play, and the good news is that the travel rates are still quite low. I was playing with this data for an unrelated project the other day. This is the number of people processed by our friends at the Transport Safety Agency or Security Agency, I don't remember, in the US daily. And this is 2019 in red and 2020 in blue. So the lowest dip here is, I think, if I remember well, I computed it, it's about 3% of what it was the previous year. And even though traffic has re-increased, it's still much, much lower than it used to be, which means that one of my components in the computation of lambda is still much lower than it used to be. Okay, so as a conclusion, what I did here was look at the risk of successful importation as a function of the rate of case importation and the intensity of local public health effort. Okay. And what we see is that the mean time between importation, or the rate of importation, is really what drives the risk. Okay. if you go towards the left of that graph that I've showed twice or 3 times, if you go towards the left here, a successful importation becomes more and more likely. However, RT brings you down and mitigates the mitigates the risk by making the consequence of importation not as bad. Okay, and quarantine, that's my last point, quarantine has the effect of lowering the rate of importation or raising the inter-arrival, the mean inter-arrival time. And I think that's it. Yep.
Thank you very much, Julien, for this very interesting talk. So now we proceed to questions. Colleagues, do you have any questions for Julien? So I think just simply unmute your microphone and ask directly to our speaker. Or if your microphone doesn't work, maybe you can write on the chat and I'll read it. I have one question, if I can. Yeah. So I noticed that actually in your model, when you do the sensitivity analysis, you mentioned that the coefficient pi is the most important one. But I would think that that's quite intuitive, right? Because pi is what branches the model into the 2 parts of your model, right?
Yeah, definitely.
Okay.
But we weren't expecting that it would be that critical. And so we've done a lot of work. I mean, we were expecting that it would play a very important role, but that it would be that important was a little bit of a surprise. I mean, another component of the work we did was to, we ran a daily estimation of parameters for that model in Canada, for each province in Canada, with different time periods. We were not trying to fit the entire epidemic curve to one parameter set, but so we have different times. And what we see is that there are some provinces where the fit for pi is actually quite good and doesn't change a lot. But there's others where pi is just all over the place, which in my view is indicative of the fact that it just doesn't know what it should be because it's so sensitive to it. So you put, the model is non-identifiable, of course. Yeah. And so you put pi to some value and you find some parameter values that work, and you put another value and you find a whole different, so it just goes everywhere.
Yeah, but in this case, I thought it was different because when you do a sensitivity analysis and you have rates dictate the flow between compartments, and you know that they're going to play an important role in a given time scale of the model, in the evolution of the model. Well, this one, it branches the model into 2 parts, and actually the force of infection depends actually in which part of the branch you are in the model. That was a bit my intuition. So one would expect that in principle, I would think. But I know, I agree with you. Yeah. Very good. More questions? So what is the next thing that Julien, you are working on regarding maybe in Canada as application or maybe theoretically?
So this one, the funny thing is, so this one is a bit theoretical. I mean, in the sense of I've talked with people from those locations that I was mentioning, and they're very interested in the work, but it's true that it's not hands-on. One of the main problem, I would say, I was talking to one of the people from PEI a couple of weeks ago, and he was pointing out that if you think about quarantine, for instance, it's not as clear-cut as I make it to be here. Here I'm idealizing quarantine. So what he pointed out, and actually there's articles in the Canadian news that really echoed this, is that there's not one quarantine, there's a variety of quarantines. So for example, in Prince Edward Island, apparently you can have, and that's quite interesting, I did not know that, you can have a working quarantine if you're a public health worker, so healthcare worker. So you'll come into PEI to help with the hospitals and so on. So you'll come from another province. So you're supposed to, in Canada, unless you're coming from, for example, the Atlantic bubble, you're supposed to quarantine for 14 days from even other places in Canada. But healthcare workers, they can go to work during the day. Well, I mean, when they're working, they can be in the hospital without a quarantine. They do get tested intensely. So they will be tested between 0 and 2 days, 4 and 5 days or something like this, and 10 and 12. But nonetheless, they go to work. When they go home, they are supposed to quarantine. So they call that a working quarantine. So in a way, these people, they're not completely withdrawn from the population, as we're assuming in our quarantining model, because they're still making contacts. We're assuming they're very careful and etc. So in a way, now we'd like to sort of introduce more heterogeneity in the quarantine behaviors, because and for example, another aspect is, you know, what the situation is like in the US. Canada is extremely dependent on the US for things like food. For example, here in Manitoba, we grow very little. We grow a lot of wheat, which we export. We don't grow a lot of anything else. So most of what we have is actually imported. Truck drivers coming from the US, whether they're Canadian or American, they don't need to quarantine. They're supposed to be very careful. They don't interact with the general population, but still they come in. So there's no quarantine for them. Mm-hmm. So if you're thinking about importations, you can't think of quarantine as being this sort of homogeneous barrier that people have to cross, because actually what happens is some people just go right through it. And so that's what we want to look at.
And how are you going to tackle that? So you're going to do like a multi-group model where you are
exactly. Yeah. That would be
profession, because I think you know, depending on the profession, they quarantine in different ways. For instance, essential workers, they quarantine in a given way, drivers, and things like that. Or you have another idea in mind?
I'm not sure. I think for that problem, I'd like to. It's been interesting working with public health authorities. I've actually been quite pleasantly surprised, I would say, by their willingness to consider theoretical models. I mean, you have to speak to them. You can't just put a theoretical model out there. But if you say, for example, I have a model where I have two types of people, and one does this and another does this. And this is the impact that I expect to see. So they won't take it like the gospel in terms of what you're saying, because you are not fitting to data or anything like this. But the ideas underneath, you toying with this and showing that there could be an adverse effect is something that they might take upon, which has been a pleasant surprise. I mean, this model, for example, I've done a lot of other work on COVID, which was much, much more applied and used data, etc., which people were happy with, but this people are also happy about, and this is a bit of a surprise to me.
Actually, I find that also that's surprising, right? That you would present just theoretical model and they're okay, very good. Questions? Fernando Saldaña, you have a question? Please go ahead, unmute your microphone and ask directly to Julien.
Hi, Professor. Thank you for your talk. I have a question. I have read several of your papers, past papers on metapopulations, and I was wondering if is it possible to use some of them to study, for example, vaccination, like a specific vaccination according to patch characteristics, so that you can give some qualitative insight about how to vaccinate people or something.
Yeah, so some people have done that. I've seen one or two papers that have done that. I can try to dig. I'm actually writing a little review right now on this type of thing, and I can dig out the reference. I remember I think it's a paper, I know Longini is inside and a few others. It's an American group. Yeah, you can definitely use metapopulations to consider this. I haven't so much. I decided to really focus on the spatial spread and the risk of importation. Because, so I don't know what it's been like in Mexico, but in Canada, there's this PHAC-led group that has sort of coordinated work of people. And, you know, I decided to focus on that aspect. So I've been using metapopulations, but not with a control of the spread in mind. I've been using it in terms of predicting the locations that would be impacted next. But yeah, no, definitely it's feasible. Yeah.
Okay, thank you very much.
Thank you, Fernando, for the question. Colleagues, any other question?
Hi, may I ask a question?
Yeah, Nancy, please go ahead.
Okay, thanks, Professor. Sorry, I just came late, so you might already explained the answer to my question, but I would like to know what kind of qualitative information have you done in the matrix, transition matrix, because can you go back to your slide in which you show the matrix?
I think I should be able to. Let me, am I on the slide here? Do you see the?
Yeah, but okay. Well, if not, yeah.
This one?
Yes, yes, yeah. I think yes, that one. So have you done any qualitative analysis of that matrix, and that analysis, what kind of information gave to you?
Well, so that part of the model, there's no real qualitative analysis here. I mean, as I was pointing out, so what happens is that that's when we're considering quarantine. And so what happens is we turn off propagation. So the model becomes completely linear. And that's why we are able to get this nice ODE that governs the evolution of the probabilities. If we had transmission, it would be more complicated. But here, the matrix has a very nice shape. We just throw it in what you call it, a numerical method for computing matrix exponentials, and we get the results.
Okay.
So, but it's due to the linearity because we shut off transmission.
Okay, and so sorry, because I think I missed that part. Why did you take transmission off in this case?
Because it's quarantine. So I'm putting you in a house and you cannot infect anybody. So yeah, and I'm just considering your movement through the epidemic model as compared to you transmitting to others.
Okay. Yeah. Okay. Well, thanks, Professor.
Thank you, Nancy, for the question. Any other questions? If not, I have a quick one. Another one, if I can, Julien. It's just slightly technical. Am I surprised that your basic reproduction number for your model is so simple? Can you tell me which models you identify as which compartments you identified as infected compartments?
Infected are the L's, the AIs, and the A's.
Right, and the basic reproduction number was too simple because I guess that the next generation matrix must be complicated, right?
It is. Well, it's a 6x6, so but it's because it's very linear. Again, I mean, once. The good thing is the arrows are quite unidirectional. So in a sense, the matrix, I can send you the original paper in which we looked at the ODE model. I'll send you the link and you'll see the computation is quite simple. It's, but it's mainly due to this linear structure, which makes everything easier.
Okay, very good. Okay. one last question, and if not, I'm like Julien. I'm old-fashioned, so I will ask everybody to unmute the microphones and just upload the speaker. Thank you very much, Julien.
Thank you for having me. It's
very good. So Jorge, we have any announcements for?
Well, no, just to thank Julien. And next week, no, in 2 weeks, we have, I think, Mario Santana.
Mm-hmm.
And then 2 weeks later, Jonathan Dushoff. So see you there. Thank you very much for being with us.
Thank you very much to everybody. Bye-bye. Thank you, Julien.
Thanks for the invite. Bye, everybody.
Nice to meet you. Bye-bye.
Bye.